Here we go. So we got chapter 16, the last part of chapter 16. I've taught you so far what normal distribution is. I taught you the standard normal. I taught you the 3 skills that you needed to take out of it. We used the 3 skills and the properties of a normal distribution to solve problems. So yesterday's session was about B and C, really getting used to it. And now today, I'm going to do application of normal distributions, which really is the same thing. It's just now you're reading into the problem. You have to think about, well, what am I finding? Am I finding the area? Am I finding the z values? Am I finding the x values? Sometimes it's like a puzzle. And your job is to figure out what I need to solve the next piece of the puzzle. Okay? That's what the application part is. And then finally, linking between binomial and normal. What's the conditions, or when can you link 2 together? The other class, Daniel in the other class, happened to cross by this because he was just playing with his CAS, and he noticed something about binomial that it actually happened to be normal. And he asked in the last class, he said whether that was a coincidence or not, and it isn't, and there is a reason. Logically, it makes sense as well. But you do, that's on exercise 16, and I'll do an example of that so you can see what I mean. And that concept is also in chapter 17, where normalize can also then be, actually you can normalize a sample as well. Okay, they're all interrelated. Okay, but here we go. Let's do an example here. Okay, so let's have a look at this. So we're meant to be doing applications now. So we know it's normally distributed because they tell us. They say the time taken to complete a logical reasoning task is normally distributed. So you already know you're dealing with normal distribution. They say with a mean of 55 seconds, so they told you the mean. They tell you a standard deviation of 8 seconds. So you know it's being measured in terms of time. Time is a continuous variable. So it makes sense that because it's continuous, you're talking about the area under the curve is the probability, and it just so happens that this curve is a normal distribution. Okay? We got mean 55, standard deviation of 8. Now it says find the probability, correct 4 decimal places. So you're using your CAS, that a randomly chosen person will take less than 50 seconds to complete the task. And before you answer that question, it's all about thinking about the problem and what is the question asking. Because if you know what the question is asking, then you can answer it. If you don't know what the question is asking, then you can't really solve what you don't know. True? So, when it says find the probability that a randomly chosen person will take less than 50 seconds to complete the task, essentially, what am I asking right now? Essentially, what am I asking? Yes, Will? Yeah. X being the measurement of what we're measuring at this moment. And what are we measuring, Aaron?
Point. I'm not sure what the ruler said, so I'm not repeating it, but I was just thinking of the area under the graph.
Very good. Will said probability of X less than 50 is essentially what we're asking. You said if we have a normal distribution, you're just saying it's less than 50, right? So let's say 50 is here, you're just saying area less than 50. What I asked was, when Will said X, what is X representing? Because remember I said the most important part of probability is defining what X represents. So what's X right now? So when we say X less than 50, what am I really talking about? What is X representing? Xian?
What? Probability? No, it's the time taken.
Time taken for what?
To finish the question.
Good. Yeah, that's why it makes sense that we say find the probability. So PR is probability, and then this says randomly chosen person will take less than 50 seconds. That 50 seconds is what we're saying in less than 50 seconds to complete the task. So what is X representing? It's the time to complete the task. And so understanding that problem, so that when you start doing conditional probability questions, it makes sense. But if you don't know what the question's asking or what the variables are representing, one, you can't put it into a notation that you're familiar with, and therefore you can't solve it as you would with them. Okay? So, probability of X less than 50, yes, you're right. We are graphically, we're just looking at this area here. We know that the mean is at 55. That's why they told us. They said mean 55, standard deviation of 8. Okay, so the question is, how do I find it then? How do I find the probability of x less than 50? Trent, where would you put in the calculator? Very good. Out of the 3 skills, one was to find area, one was to use the area to find z or x, and one was to transform, or at least change, between x and the z values. Okay, so out of the 3 skills, in our case here, we're trying to find the area, which you literally just type in norm, CDF. What would I be writing? What's in norm CDF? What do we need? Yes, Trent. Good. So what's my interval?
0, negative infinity.
Not negative infinity. What?
You can.
Negative infinity to 50. Yes, sorry, I heard infinity. Yeah, to 50.
And then, I don't know what's more,
55.
Good. Mean and then standard deviation. Type in your CAS and you'll get the answer. Alternatively, if you didn't know you could do norm CDF, what is the long way of doing this? Anna.
You can put the mu and sigma values into the normal distribution function, like the 135 times sigma times, yeah, and then negative power negative half x minus mu all over sigma, and then type, yeah, close my thing. And then type that into the calculator.
Yep. Very good. You're just missing the squared there. But yes, you would sub all the values in and then you do what?
To the integral from negative infinity.
Perfect. Essentially, when you're doing normal CDF, remember we're still doing a curve. It's still continuous, like chapter 15, continuous data. So it is continuous data, we're finding the region. How do you find the region? Integration. So if I integrate from negative infinity up until 50, and I replace the standard deviation and I replace the mean, and I type this in and I define that function, and I did integration of this between negative infinity up to 50, it will be exactly the same answer as doing normal CDF, mean 55, standard deviation 8, and integral. That's essentially what you're doing. Okay, so you're just finding the area. Cool. So we do that. That will give us. There we go. It'll give us 0.2660. So what does that tell me? What's the probability? They said round to 4 decimal places. So make sure that you round to 4 decimal places. It's about 26.6%. Okay. Next question. Find the probability correct to 4 decimal places again that a randomly chosen person will take less than 50 seconds to complete the task. So it's the same thing. If it is known that this person took less than 60 seconds to complete the task.
Probability of like the probability of 50 over the probability of less. Yeah, the intersection over the probability of x being less.
Okay, good. What are you doing right now? What kind of probability are we doing? What's this?
I don't know by the line.
You know it by the line. What's the name for this? Yes. Oh, yes.
He says correct.
Even as the whole thing.
It says correct for decimal places. It doesn't. Something is correct up to 4.
Yep.
You can be correct up to 6. That's the 5. Doesn't actually say round. Right?
Oh.
I
Mathematically, when we say correct to, we imply it's round to. Round to 4 decimal places. Okay. What was the name for this probability that Trent was just talking about? He said probability of x less than 50 intersect with x greater or less than 60, and he said over x less than 60. What are we doing here? Conditional. This is called conditional probability. That line that Trent was doing with his hand is called the given symbol, the given sign. Okay, so essentially you're really saying what's the chance of x less than 50 given that x is already less than 60. we know that from chapter 13 that this would be the intersection of less than 50 with the intersection of x less than 60 divided by x less than 60. That's the PR. That's what we're looking for. Okay? So logically, x less than 50 intersects with x less than 60, where would that be? Where would it be? No, not 50 and 60. Picture it. Always picture this. Less than 50. If you draw it, less than 50, less than 60, where do they both intersect? It has to be less than 50. So another way of writing this answer is probability of x less than 50, which we already got, and probability of x less than 60, which we can find. Okay, so both of which we can do. Type it in your CAS, norm CDF, which you already got for the top one, and norm CDF with negative 50 to 60, and we're down. You got A and B. See, all I'm teaching you is 3 skills from chapter 16, but you really just have to understand the problem. Draw the problem, figure it out. They'll give you a piece of puzzle, and your job is just to put them together. Okay? Let's try another one. Let's try this one. This one might get you a bit thinking. Well, get you thinking a bit. Try this one. Limits of acceptability. So it means like there's a limit to what you would be able to accept. Okay? Is imposed on the length of a certain batch of metal rods. Okay, so you got these metal sticks, and there is a limit to what you would accept depending on the length of it, right? So you got between 1.925 to 2.075 centimeters. It is observed that on average, 5% are rejected as undersized and 5% are rejected as oversized. So it's either too long or it's too small, right? Then, assuming that the lengths are normally distributed, so now you know, okay, it's normal distribution, remember lengths is a continuous variable, it's not discrete, okay? So we already know this is a continuous data, it's normally distributed, find the mean and standard deviation. Draw the problem. Draw what you have, what are you trying to find, and see if you can solve that. Okay, because essentially I've taught you everything from chapter 16 so far. I just need you to think about it. And that's the tough questions you can expect when you're doing multiple choice questions in an exam. Just think about what are they asking? What am I trying to find? What have they given me? That's probably the better start. What have they given me? What's the 5% rejected, 5% undersized? Can you model it? And what was the hardest part of this whole chapter? Is defining what X represents. If you can define what X represents, you know what you have to do. Okay? So have a go with that. I'm going to give you, well, let's go with 3.5 minutes. I reckon 3.5 minutes to give this a go. 3.5. Draw the problem. What's the 1.925 and 2.075 representing? Why do they tell you that? What's the 5% rejected and 5% rejected, oversized and undersized? How do I use that to find the mean and standard deviation? About a minute left. All right, let's have a look. Someone tell me, what was the first step, or what is the... Anyone figured out what 1.925 and 2.075 is representing? What is it telling me? Anna? How do you know that? Yep. Very good. Excellent. And because it's normally distributed, that's why you can say that. So we know that less than this particular point, so less than 1.925, you have 5%. You have more than 2.075, that was 5%. And you know it's normally distributed. So I've just drawn the problem based on what they've told me. They said normally distributed, 5% rejected, 5% rejected, oversized and undersized. And that's what I did. And they gave me an interval of what they would accept. So what they would accept, which is that white region, which I haven't colored in, this region here, that logically would then have to represent how much percent? 95. Oh, sorry, 90%. Sorry, it's not 2 standard deviations. Sorry, in my head was thinking 2 standard deviations. That would represent 90% because it's 5% and 5% on each side. So now that you know this is 90%, okay, your job, again, remember, is to find the mean. So we don't know what the mean is, and we don't know what the standard deviation is. So do we do? So that's the first step. So I've just drawn the picture, got an idea now. What do I do now?
So it's so the midpoint between 5%, like the midpoint to 1.925 and 2.075 is going to be 50% exactly, or the mean.
Yep.
So if we find the midpoint between 1.925 and 2.075, by the end that's get 2, which is the mean.
Very good. Because we know it's right at the center, then because it's symmetrical, this was 5%, 5%, so the mean, which is right at the center, if I found the total length between 1.925 and 2.075, and I halve it, that should give me the x value, which is the mean. Okay. Second question is, what is my x-axis representing? What's the variable representing? The length. Good. It's the length of the rods. Okay, so now you've got the idea of length. Obviously, it's continuous, hence why it's on the x-axis there as the variable. Okay, so this was one way to do it. You got 1.925, add with 2.075, find the total distance, and then halving it. So that's really finding the average. Okay. Whoops. What's the average there? That's what? 2.5 plus 7.5. That's 1, 1. Is that 3 on 2? 4 on 2, is it? Yes, you're right. It's just 2. So I now know the mean is 2. Okay? So knowing the mean is 2, how do I find the standard deviation? Yes, Aaron.
If you make the z-score, like the version z-score for z equals actual value, take away mean on standard deviation. We know the mean now, and if you sub in the actual value as like say the lower limit, like 1.925, and we have the percent, like the area from the left up to that limit, which is 5%. You could fill in, you could find the z-score, and then find the standard deviation.
Yes, that is correct. Okay. Alternatively, there's another method which you're right. So that is the one way to do it. And that's how you find your standard deviation. You're right. You know that up until this point, remember inverse normal, you can use the z value or find the z value equivalent to it. Or at least you know this is 5%. So you would be able to find the z value. Just be careful when you use inverse normal. It only calculates from left to right. Okay, so if you want to know the z value corresponding to 1.925, then it's easy because that's 5%. But if you wanted to know the z value of 2.075, okay, then you would have to make sure that you're actually looking for the area of 95%. And that will give you the z value here. Okay, Aaron.
When you go for the z-score there, like the area is 0.05 when you enter it in.
Yep.
Is the mean and standard deviation, because it's in z-score, do you change it to 0 and 1, or do you keep it as this?
Perfect. 0 and 1, because when you're doing inverse normal, you are relating to, you don't know anything about the current x star, so you're missing out on the mean and standard deviation, so you can't use that. But the nice thing is the area is proportional to the z-axis. So when you do the inverse normal, you'll be using 0 and 1, and say what is the z value, because you're looking for z value, so you're using the z properties. So the z properties are mean of 0 and standard deviation of 1. Okay? Once you know what the z is, then you can replace the z with whatever value it represents for 5%, and then you know the x represents the equivalence for 5% or z value, and you know the mean, which is what you calculated was 2, you can find out standard deviation. Okay? Alternatively, let's say you didn't recognize that the mean was actually the center. Okay? The way that the textbook would have wanted you to do, or how you would want, they wanted you to do it, was like this, and I'll show you what they want. This was the quicker way to do it, which you guys put it all together, which is great. But the actual way the textbook wanted you to do, which was this. They wanted you to simultaneous the problem where z equals to x minus mu over standard deviation. You don't know what mu and standard deviation is. There's two unknowns, right? But they did give you enough information. They gave you an x value, and they didn't technically give you a z, but they gave you an area to find z. Okay? So when it's 1.925, I needed to know what the z correspondence to that is. I knew this was 5%. So I could do inverse norm, type in the area. The area was 0.05, standard deviation, mean is 0, standard deviation 1, and this will tell me what the z value equals to, based on the area. Okay? Okay, so let's try that. So I'm going to go to my CAS. Let's go to CAS. I'm going to do inverse normal, menu, 5, 5, 3. So what's the area? I know it's 0.05, 5%. This is mean 0, standard deviation 1. So this will give me the z value that corresponds to 5%. And that's negative 1.6448. Okay, so that's what I know. Now I know that I've got one equation, negative 1.64485 is equal to 1.925, take away the mu, divided by standard deviation. That's my first equation. Okay? If I can get another equation with mu and standard deviation, I can now simultaneously solve them on your CAS. Okay? So what's the next information they gave me? They said at 2.075, there's also 5% in the top region. So here, I have x equals to 2.075, but I don't know what z equals to. I do know the area up here is 5%, but remember when you do inverse normal, it only calculates from left to right. So if I calculate the area is not 5%, but in fact it is all of this region here. And that tells me what area would this be? What area would that be? If you know the top end is 5%, then the leftover has to be 95. So that's why when I do the inverse normal to find the equivalent z value, I would be doing inverse norm for 0.9501, and that will tell me the z value that corresponds to a 95% interval. Okay, so I do the same, and you should expect it will be exactly the same value. The only difference is it's positive. So if I change to 95, it's the same value as positive because it's symmetrical, right? So now I know I've got my second equation. 1.64485 is equal to 2.025 or 75, sorry, minus mu divided by standard deviation. Solve on your CAS. Type in solve those two equations to find mu and standard deviation, and you would have been able to solve it. So if I just type in my CAS now, I do solve, and I'm going to type in two equations. I'm going to do two equations. I had negative 1.64485 equals 2 x minus, I'll call it A for mu, B for standard deviation. Okay, and x was 1.925. Okay, and then my second equation was 1.64485 is equal to, and then I'll do the same thing again, 2.075, take away A, divided by B, solve for A, solve for B. Okay, so I got my two equations there, got two unknowns, press enter, and voila. A equals 2, A is your mu, and you got your standard deviation, which is 0.045, but unless they told you to round it to some decimal, no, didn't really say, no.
When you use the inverse normally,
Yep.
so the first part is the area corresponding to just any normal distribution, not the standard normal.
This one up here?
Yeah.
That one, no, this is corresponding to the Z standard normal because I've got a mean of 0 and a standard deviation of 1. So I'm, yeah.
Yeah, but then the area is on the other graph, the other normal, not the standard.
Yeah, but both of them have the same area. So the idea is that your current data X, right? That's the reality. Reality is that you still have 100%. Ideally, you also want 100%. But you want to know that my 5% in my class, what is that relative to the ideal 5%? So I might say if you are 1.9, that is my 5%. Less than this is 5%, right? Then I'm just asking, well, if this was 5% for the ideal world, then what would the X value be, or in that case, Z value be? So because they're both normally distributed, they're just skewed in different ways, but they both have the same area. It's still 100%, still 100%. So when I say 5% here, what's the boundary up to 5%? It was 1.9. So the question is, when you're doing inverse normal, you're asking what's the boundary for the ideal world? What's the Z value that corresponds with the exact same proportion? Because it's exactly distributed normally. So they're both distributed normally, it's just that this is more ideal because the mean 0 and standard deviation is 1. So we're using that 5% Z value to solve the problem. That's what we're doing.
Earlier, so just copy the exact inverse normal data because it's not exactly 1.64485. It's like more than 2 times. So you should have copied it.
I should have copied, yeah. I noticed that when I did it, but I was hoping that this would be close.
I mean, it's not exactly the same actually.
Oh, not exactly. Yeah.
No, it was exactly.
Oh, it was exactly. Well, yeah. So that's why I typed in as many digits as I could, because I could have stopped around 1.6, and that would make a difference. The reality is I was meant to take more, but that means I had to go back and change my settings to take up more or copy the whole thing down. And I didn't want the whole equation to look messy, so I just copied that to that. But you're absolutely right. If you're doing an exam as a test, it's why it matters the number of decimal places that you take. And the more you take, the better. Okay, the more you take the probability, and it's better to take exact. So your final answer is when you round it, but you don't round it in between. Because if I had rounded it here, that would round this answer, and therefore my answer would be even more rounded. And then finally, I'll round it again. That makes it worse. Okay, so always take the exact values as you're solving. Your final answer should then be rounded. Okay, get your final answer, then round. So yes, in that step there, I was meant to copy this down here, and then copy this one down here before I solve this. But yes, that's what your textbook wanted, just to apply this sort of simultaneous equation. But you see, at the end of the day, the better you draw the problem, or the better you can visualize what's going on, it's actually pretty easy to do. It's just piecing things together. Okay. Now, just before the class ends, I'm going to just teach you the one last thing you need to know. very easy concept. Daniel in the other class, he was playing around with the binomial stuff. It's in chapter 14. And as he was playing around with it, he was changing the number of trials and then the probabilities. And what you find that it doesn't matter what the probability is. 20%, 20%, 50%, 50%, 80%, 80%. Normally you can tell one's positively skewed, symmetrical, and then negatively skewed, right? What happens is, which I'm showing here, if you do 10 trials, means that whatever that binomial example is, if I flip a coin, that's binomial, right? If I flip 10 times and I know there's 20% chance of getting what I want, then it'll be skewed towards the side where it's positively skewed. Okay, the tails, the positive, pointing into skewed in the positive direction, right? If it's 80%, you would say the tail's being skewed negatively, to in that direction. But what you'll find is when you start increasing the number of trials, so what, you go from 10 to 20, it's looking still similar. Yes. If I start increasing it now to 50, and then now to 100, it doesn't matter where the percentage is. In terms of the x-axis, it will change. The x-axis will change, right? But the data in itself becomes more normalized at that point. Okay, so it's still 80%. It's still 80% of 100. So if it's 100, 80% of 100 is 80. Okay, it's not 50 and it's not 20. Okay, so at 100 trials, 20% still, you still have a normalized section. It's still skewed in that sense, but it's normalized here. And what they're saying is, in a hypothetical sense, if you could trial infinitely, if you could trial very large, like 1 million, what happens is this binomial, which is discrete data, actually can be modeled or can be predicted using a normal distribution. Yes. So that means if you have a continuous data, you can predict what it would be for a discrete problem. Okay, or if you have a discrete problem, you can predict it using normal if it's a large enough trials. That's the idea. So that's essentially what the last part of it is how binomial and normal can be related, and it's the idea that the more trials you do, it starts to balance itself out, where the peak is what you expect, which is what n times p is. It's what you expect is the highest point. Okay? The more trials you do, it will start to model it. But obviously they're both different variables. One is discrete, one's continuous, but you can model it and say, oh, if it's large enough, maybe it's normalized. And it does show that. Okay? So, this is what, wait, where's this part? Whoops. That's what this is trying to say here. They've got a figure, the dots is your discrete. Dots are your discrete data because you can count them. The model that you see is a distribution, it's a function. Okay, so it's accounting for all possible data in between. What is it again? No, it's not here. There was a question of how big does it have to be considered big enough to be normalized. There is one small property in your textbook hidden somewhere. I can't remember what it was. I'm going to go find it again. It was something like n times p had to be greater than or less than a certain value. If it's greater than a certain value, you can say it's large enough. It comes up again in sampling. I'll find out that property and I'll let you know. But for the sake of this exercise only, at this moment, any of these questions would be large. Okay, so I want you to have a go with this one. It says a sample of 1,000 people. Okay, so you got 1,000 people from a certain city were asked to indicate whether or not they were in favor of construction of a new freeway. So you're either in favor or you're not. So that's clearly binomial. Yeah, so it's yes or no. You're in it or you're not. Okay? It is known that 30% of people in this city are in favor of the new freeway. So 30% are in favor and therefore 70% not in favor. Okay? Find the approximate, that's a key word. This is when you know you can use the approximate of normal to predict what binomial would be, provided they don't give you enough information. Okay, so here we go. We've got find the approximate probability that between 270 and 330 people in the sample were in favor of the new freeway. Okay. What is that asking there? Just that last line, what is it asking? What am I trying to find?
Between the 60 people in favor of highway.
Say it again.
I mean, we need the 60 people.
What's the chances? So PR of 270 between x between 270 and 330 is in favor. Okay, you want to find the chances of that. Now you can do that using binomial CDF. You can add them all together, all the probabilities of 270, 271, 272, 273, all the way to 330. Okay, you can add all those together, find the approximate probability. You can do that. So that's what I did. I said binomial method, X, I defined it as in favor of the new freeway. I know N, number of people, number of trials, so how many people am I surveying? There's 1,000 of them. And then this is what I'm trying to look for. Now, it was either, because it does matter in discrete whether you include it or you don't. Because if you don't include it, you don't have 270. If you do include it, you do have 270. It does matter. Whereas in normal distribution, it doesn't matter. True? It doesn't matter if you include it or you don't. So here, I've calculated 2 of those regions there for you. So I did binomial CDF, calculates between 271 to 329, because I'm not including 330, it's less than that, and you can only count 2. So it's 220. 329 is up to that point. I don't include 330. And I calculate, I get 0.958292. Then I do the same for binomial CDF, where I do include 270 and 330, and I get 0.96 or whatever it is. Yes? Yeah, and that, yes. So it would mean, between would be that you don't include it. And that's where I'm a bit reluctant. I don't know, because sometimes the examiners will write between, thinking or assuming that you should know it's inclusive or not inclusive. And that's a bit, I don't know when, yeah, I would agree that when they say between 2 numbers, you don't include the numbers. It's just between those 2 boundaries. But it is, some questions sometimes yes, sometimes no. So it's kind of hard to tell when. It's kind of like that question of, if you have 15.5 cars, do you say you have 16 cars or you say 15 cars, right? Logically, you would say you have 15.5 cars. So do you only include up to 15, or do you round it up and say it's 16 because you can have 16 holes? If it's 15 is too little, 16 makes sense to include 15.5.
It's pretty much the norm.
Yeah, norm. Yeah, and so a lot of the times I would say if it's a individual thing that you can count, you round it up, because it doesn't make sense to have less than the amount. So the only way to get the amount is to get more than that. So more than 15.5 would be 16. But I have encountered exam questions where they've rounded it down. So that's why I don't know. It's one of those questions where do you round it up, do you round it down? I will always do it the way I think that makes sense, and hope that the examiners would go for the same thing.
Yeah, but for the karma, I reckon you need to have a round down. If it's not up, you have a 4, have a half a car.
In that question with the car example, the examiners was talking about how many cars would return to Melbourne or Sydney. And if we said 15.5, they said round it down to 15. I'm assuming because it's number of cars that are being returned. Yeah, which is weird because I feel like it should be 16 would guarantee that you have 15.5. If it's less than that, then it doesn't make sense. But it's dependent on the question, as you were saying. Yes.
That's like how much you have. You don't actually have 15.5. Like you have 15. So like even 15.9, you still have 15, but you don't have 16. But you have.
Yes.
So like even 15.9, I'd still say 15 because you don't actually have 16. Which is why you round it down.
It's just that because a lot of these questions, when you calculate, they'll say when will you have X amount, like it's an intersection. But if the intersection is at 15.9, then yes, you're right that the only amount that you have is 15, but technically that amount is less than what you needed, because equal is here, so they say at least.
It's like when will you have this? Then round up, because below you don't have it, but above you do have it.
Yes.
But if you have 15.9 of something, you don't have 16, you still have 15.
Yes, that is true too. To put it forward, I don't actually know when it will be like up and down. I've always gone with if it has to be holes or if it's something you have to have. I've rounded it up hoping that they don't argue and say the other way that it has to be down. But I don't know. It's very. Yes, see if they did it like that, that's much easier to answer the questions. They say rounded to the nearest whole car, then that makes it easier. But I think it's when you're doing extended response questions, they can't say that. They can't say round to the nearest. That's normally a short answer question, which is why exam 1 should have been easier to answer that. Extended response is now kind of like, you play around with that. Yeah. But anyways, here we go. If we did the normal distribution way, what I've done there is, if n is large enough, and there is a property that you, in your textbook, it's not even highlighted, but there is a property to determine when n is large enough, then we can approximate the expected value, okay, because we know the expected value, which is the mean, is the very largest point what you expect, which is n times p. Okay, that's from your binomial there. Then n times p, and you would then know how to find variance because it's np minus 1 minus p, yeah? So that's what I've done here. I've got your expected value is 300, standard deviation I've worked out to be root 210. This is what I'm trying to find. Okay, I'm trying to find x, 270 to 330, and you can do norm CDF. You got your interval, lower bound, upper bound, and you find that they are similar, which is in between these two. In between. So it's an approximate, only given that n is large enough. And there is a property to determine when it's large enough.
What's the property?
Yeah, I forgot. It's somewhere in your textbook. It's like n times p has to be. I remember there's a 5 in it, so it's like less than or greater than 5. If you times these two numbers and it's less than 5, bigger than 5, then it is considered large enough. But funny enough, it's not highlighted. It's not highlighted in your textbook, but I did go through your study design and it's there. It's in your study design, so I think you should know it. But yes, so the question is, when will it be large enough? But theoretically, or conceptually, what you need to understand is when it's big enough, the sample's big enough, you can use binomial to approximate. Okay, that's all you got to take out of that session. Okay?
Based on the study design, and you think we should be doing it, but we have no idea, and we still